Hello students, welcome to my YouTube channel. Students, today we are going to discuss a very interesting topic of self-induction. In the previous lecture, we have discussed about the laws of electromagnetic induction. Then we have also discussed the Lenz law, right? Now it's time to discuss self-induction. So for that, what we do is, let us consider a coil. Suppose this is a coil. Let us consider this coil to be having n identical turns. And let us consider this coil to be connected to a battery. Battery is a combination of cells. And suppose this is a tapping key. This is the positive terminal and this is the negative terminal. So what we have assumed is, consider a coil connected to a battery and a tapping key. When the key is pressed, what happens is the current will start growing along this direction, isn't it? The current starts growing through the coil, and as a result, the magnetic field lines will also start growing through it. This in turn will produce induced current or induced EMF in the coil. And as per Lenz law, the direction of the induced EMF or the current is opposite to the cause that produces it. It's always of opposing nature. Now students, when the tapping key is released, then what happens is the current in the circuit starts decaying. It starts decreasing. And as a result of this, the magnetic field lines linked with the coil will also start decreasing. Therefore, the induced current or the induced EMF so produced in the coil, it opposes the decay of current in the circuit because of its opposing nature. Thus, we find that when the key is closed, that is during the growth of current, and when the key is released, that is during the decay of current. In both cases, an opposing induced EMF or induced current is produced in the coil. Now, this phenomena of producing an opposing induced EMF or induced current in a coil as a result of change in current or magnetic field, or more generalizing, you can say as a result of change in the magnetic flux linked with the coil, as a result of change in the magnetic flux linked with the coil. Is known as self-induction. Right? So, in this coil, during the growth of current as well as during the decay of current, due to the change in the strength of the current flowing through the coil, the magnetic field linked with the coil changes, and accordingly the magnetic flux linked with the coil also changes. And as per the phenomenon of EMI, an opposing induced current is produced in the same coil. So this phenomenon is known as self-induction. Now, as I've stated, students, self-induction opposes both growth of current as well as it opposes the decay of current. Now, when the tapping key is pressed, the current will grow along this direction. This is the applied current. So as a result, the magnetic field lines through the coil will also start growing like this. So what happens is, due to this increase in the magnetic flux, an opposing induced EMF tends to get developed in this coil, which tends to oppose this growing current. Similarly, when the tapping key is released, these magnetic field lines will start winding up So as a result, now the direction of the induced current in the coil will be such that it will oppose the decay in the current through the coil. So in both cases, whether the growth of current is considered or the decay of current is considered, in both the cases, the induced EMF always is of opposing nature, right? So that is the reason why this induced EMF is also known as back EMF. Induced EMF is also known as back EMF. Now students, one more thing, very important point to be noted down is, in case of a straight conductor, right? If it is not converted into a coil, in case of a straight conductor, the self-inductance is always zero. Do remember that, right? And also, this self-induction, it's actually also known as the inertia of electricity. Self-inductance is also called the inertia. It is also called the inertia of electricity. Why inertia? Because it opposes both the growth of current as well as the decay of current through the coil. So inertia means opposing nature actually. So that is the reason why inductance is also known as inertia of electricity. Now let us discuss it mathematically. Now students, as we are aware, the magnetic field linked with the coil, it is directly proportional to the strength of the current flowing through the coil. And also we are aware the magnetic flux, it's given by the scalar product of magnetic field and area vector. So it is directly proportional to the strength of the magnetic field. So combining these two, we can safely conclude that the magnetic flux linked with this coil is directly proportional to the current flowing through this coil, isn't it? So greater the magnitude of the current flowing through the coil, more will be the magnetic flux associated with this coil, right? So therefore, magnetic flux linked with this coil is directly proportional to the current flowing through it. Now, as we are aware, students, in order to eliminate this proportionality sign, we need to introduce some constant. So phi is equal to Li. This L is constant. It is known as the coefficient of self-induction, or it is also known as self-inductance of the coil. It is also known as self-inductance of the coil. Now in the subsequent lectures, we will discuss it mathematically that this self-inductance of a coil, it does depend upon the number of turns, it depends upon the cross-sectional area of the coil, and it also depends upon the permeability of the material of the core, if any. If we insert a material and use it as a core, then the self-inductance of this coil will also depend upon the nature of the permeability of the material of this core, right? So L basically, it depends on 2-3 factors. First is, it depends upon the number of turns. Second, it depends upon the cross-sectional area. And it obviously depends upon the permeability. It depends upon the permeability of the material of the core. If any, right? So these are the 3 factors on which the self-inductance of the coil, that is capital L, depends. Now let us try to define this L mathematically, right? So consider this particular equation. What we do is, let us consider to be equation 1. From first it's pretty clear that if I is equal to 1 ampere, then L is equal to phi. So this can be used to define the self-inductance of a coil, right? So students, look, this L, which is the self-inductance of a coil, is numerically equal to the magnetic flux associated with the coil when a current of 1 ampere is flowing through it. It's so very simple, isn't it? So this is how the self-inductance of a coil may be easily defined. Now there is some another method of defining self-inductance as well. For that, we need to discuss the induced EMF. As we know that induced EMF is minus L di by dt. We are aware of this formula, isn't it? Negative sign suggests the opposing nature of the induced EMF. Now look, di by dt is the rate at which the current in the coil changes. If the current in the coil becomes steady, then I would be constant, so this differentiation will be 0, so no induced EMF will get produced in the coil. So the induced EMF in this coil will last as long as the current in the coil keeps on changing. And current in the coil will change only if the tapping key is pressed during the growth of current and when the tapping key is released, that is during the decay of current. If the tapping key is kept pressed, then the current through the coil will become steady, and in that case no EMF will get induced in the coil. So students, please remember that, right? For the EMF to get induced in the coil, the current in the coil must change continuously with time. So that's the mandatory condition for the production of induced EMF. Okay, now let's try to make use of this particular definition. In magnitude, it may be written as L di by dt. Now we can make use of this mathematical expression as well so as to define L. So if the rate of change of current through the coil is 1 ampere per second, then L would be equal to E, isn't it? So students, the self-inductance of a coil is numerically equal to the EMF induced in the coil when the current in the coil changes at the rate of 1 ampere per second, right? So these are the two definitions which can be used to define self-inductance of a coil. Again I repeat, here the self-inductance of a coil may be defined as the magnetic flux associated with the coil when a current of 1 ampere is made to pass through it. And using this mathematical formula, we can define the self-inductance of a coil as numerically equal to the EMF that get induced in the coil when the current in the coil changes at the rate of 1 ampere per second. Clear, students? Now let's talk about its SI unit. SI unit of self-inductance is Henry. It is Henry, Henry. It is denoted by capital letter H. Now here, if you make use of this particular expression, so L, it would be equal to E divided by di by dt. Di by dt is the rate of change of current. So what we do is 1 Henry is equal to EMF. It is measured in volt, SI unit, and rate of change of current, that is 1 ampere per second, right? So we can make use of this so as to define the SI unit of self-inductance of a coil. So students, the self-inductance of a coil is said to be 1 Henry when 1 volt of EMF get induced in the coil if the current in the coil changes at the rate of 1 ampere per second. Again, I repeat the statement, students. 1 Henry is the self-inductance of a coil when 1 volt of EMF get induced in it if the current in the coil changes at the rate of 1 ampere per second. So there are various units for measuring self inductance. So one is millihenry. It is equal to 10 raised to power minus 3 Henry. Then another unit is microhenry. Obviously it is 10 raised to power minus 6 Henry. Now students, let us discuss the energy stored in an inductor, right? For that again, let us consider a coil, suppose of inductance L, and let it be connected to a battery. This is the battery, right? And this is the tapping key. And this is a coil of inductance L. Now, this is a source of EMF, right? And it is connected to an inductor L. Now, as the tapping key is pressed, as we have discussed earlier, the current through the coil will start growing and induced EMF is set up in the inductor, and the induced EMF then opposes the growth of current through it. So the source of EMF, this is the source of EMF, it has to spend energy in sending current through the circuit against the induced EMF. So this energy spent by the source of EMF is stored in the inductor in the form of magnetic field. So it is perfectly in accordance with the work energy theorem. Whatever work or energy is spent by this source in sending current through the coil against that opposing induced EMF will get stored in the inductor in the form of its energy. And students, the energy stored in the inductor is in the form of magnetic field, right? So what we consider is, initially suppose the current in the inductor is 0. Let us consider initially, that is at t equals to 0, the current in the circuit is 0. Right? Let us consider this. And let at any instant the current in the inductor is I, and the rate of growth of current at that time is equal to di by dt. So at instant t, suppose the rate of growth of current let us consider it to be represented by di by dt. This is the rate of growth of current in the coil, right? So we are aware the induced EMF which is generated in the coil, induced EMF in the coil, or coil is also termed as an inductor. It is given by, in magnitude, it is given by L di by dt. L, as we have discussed, it is the self-inductance of the coil, right? So, if we consider the source of EMF, if the source of EMF sends current I through the inductor, for small time dt, for small time dt, then the small amount of work done, that is, then small work done by the source in sending current through the coil against the opposing induced EMF, it is given by EI dt. Now look students, this is the potential difference, which is the induced EMF or the back EMF. This is the current and this is the small time, right? So basically where this formula has come from is, we know that the potential difference, isn't it? It is given by the potential difference between the 2 points is given by the work done per unit charge. Therefore, work done is equal to V into Q, or W is equal to V. Current is the rate of flow of charge. So I is Q by T. So Q would be equal to IT. Here, work has to be done by this source of EMF against the induced EMF. That is, in place of V, we need to write it as E. E is the induced EMF, right? And the small amount of work done dW during small time dt. So from here we can write the small amount of work done by the source of EMF in sending current I in the coil against the induced EMF for small time dt is EI dt. Clear, students? Therefore, total work done total amount of work done by the source of EMF till, say, the current increases from its initial value I equals to 0 to final value I. Total work done from initially at t equals to 0, current is 0. At t equals to t, suppose the current at that instant is I. So in that case, total amount of work done would be given by integration of Li E I dt, and limits would be from 0 to I, right? So let's substitute the value over here. E, its value is L di by dt into I into dt. So what we are left with is integration limits is from 0 to I. So we are left with L I di, right? So self-inductance of a given coil is always constant. So it can be taken outside the integration. It does depend upon various factors. As we have discussed, it depends upon the number of turns, the cross-section area, and the permeability of the material of the core, if any. But for a given coil, self-inductance will naturally be constant. So it can be taken outside the integration. So integration of I with respect to I. So that will give you L I square by 2. Isn't it? Integration of I is I square by 2. 0 to I. So upper limit minus lower limit. So what we get is half L I square. Now, as per the work energy theorem, as we have stated, this work done by the source of EMF in building up current from 0 to the maximum value is stored inside the inductor in the form of energy. Therefore, the energy stored in the inductor is given by half L I square. This is a very, very important formula. This is the expression for the energy stored in an inductor. Now students, some very, very important points to be noted down. First is, as I pointed out, the energy is stored in the inductor at the expense of the energy of the source of EMF. This is perfectly in accordance with the work energy theorem or the law of conservation of energy. So, the energy is stored in the inductor at the expense of the energy of the source of EMF, at the expense of the energy spent by the source of EMF. Right? And second is, which is again very, very important one, here the energy resides in the inductor in the form of magnetic field. Students, here we must recall the very important fact is that in case of a parallel plate capacitor, the energy is stored in the form of electric field, while in the case of an inductor, the energy is stored in the form of magnetic field, which is very, very important point. So the energy resides in the inductor in the form of magnetic field. So this is a very, very important point. Right? Here I must also recall a very, very important thing, that self-induction, as we have discussed, it is also known as inertia of electricity. Because when a source of EMF tends to send current in an electric circuit having a coil, then what happens is the self-inductance of the coil, it behaves the same way as the mass of a body does. Now, as we are aware, mass of a body, it gives the measure of inertness of a body. So, when a force tends to cause a change in its state, then the mass of a body, what happens? It opposes the change in its state, isn't it? So we know that more the mass of the body, more is the opposition it offers to the change in the state of the body. Similarly, mass of a body gives the measure of its inertia, isn't it? In the same way, more the self-inductance of the coil, more is the opposition it offers to the change in the current through the coil. Hence, self-inductance, this L of the coil, is also known as inertia of electricity. So always remember, the self-inductance is also known as inertia of electricity. So greater the value of L, the more will be the opposition offered by the coil towards any change in the current or the magnetic flux through it. Right? So that is the reason why self-induction is also called as inertia of electricity. So students, I hope you have understood this topic. So in this lecture, what we have done is we have discussed self-inductance, the definition, what actually self-induction is. It is also known as back EMF, right? Self-induction, it's known as inertia of electricity. Then we have tried to discuss the factors on which the self-inductance of a coil depends. Mathematically, we will try to validate those factors in the next episode. Then we have discussed the various ways of defining the self-inductance of a coil, isn't it? Then we have got the expression for the induced EMF. In magnitude, it's given by E equals to L di by dt. Di by dt represents the rate of change of current through the coil. Clear? And then obviously we have done the topic of energy stored in an inductor. The formula is half Li square. And the energy stored in the inductor is always in the form of magnetic field. So students, that's it for this particular session. Do join me in my next lecture then. And stay blessed.